So we are going to kick off the meeting with Lina Necib. She's going to be from MIT, and this is the only talk we have online. So she is going to talk about the machine learning of dark matter. She is the first keynote speaker, and then we are going to come back with the next talks in person. All right, Lina, it is up to you.
Hi, well, thank you so much for inviting me. I'm really thrilled to talk about machine learning in the world of dark matter and structure of the Milky Way and the galaxy. And also, I really hope that I will get to meet you guys soon at some point. If there is any interest, please don't hesitate to email me. I would love to talk. And I'm sure I'll get to see all of you in person at some point soon. All right, let's get started. If we were in the southern hemisphere, which unfortunately we're not, we would be able to see the universe or the sky looking this beautiful. So we have the disk of the Milky Way right here, and you can see some dust extinction there in the optical, which is quite gorgeous, as well as satellites of the Milky Way, like the LMC here and the SMC. My research program, though, has been kind of looking at something else completely underneath all of this, and that's dark matter. So if I had dark matter glasses, what I would be able to see is something a lot more like this. So dark matter is centered around, the center of the galaxy, around our satellites, and there are also some smaller structures all around that we wouldn't be able to see it. And although this is lambda CDM that is kind of extremely successful at very large scales, it kind of has a lot of challenges at smaller scales, which is why we don't really know as of now whether it's this or whether it's warm dark matter, in which case we would lose some of that small structure, or if it's self-interacting, where things tend to be a lot more spherical and the density is more chord, so the distribution of it is a little bit more even, or it's something else altogether. So what we would want to do is really create a map that takes us to this invisible stuff that we see. So my personal goal has been to map from the stars to the underlying dark matter. And the twist that I would like to add to this talk specifically is that we would like to do that using artificial intelligence. So there are multiple AI methods. So today's talk is going to be a little bit of a tasting menu of a lot of different methods, a lot of different parts of the galaxy. And I hope that it will kind of generate some discussion with you guys at some point. So the way that I'm going to start this is by kind of going through the AI kind of signal processor, the archaeologist, and the cartographer. And these are different methods and different technologies that we're going to use based on different differences in data. And what I would like to emphasize throughout this talk is really that we need to adapt our AI methods to the data sets that we have. So let's get started with the AI signal processor. And this is going to be kind of unsupervised learning, which means that we're not really telling it beforehand any information, but we would like to extract some of the interesting information out of it. So there is beautiful structure to our Milky Way, and the way that I would like to organize it in my head is really about the galactic center and the halo, the stellar streams, solar neighborhood, and dwarf galaxies. And the reason that I usually focus on these four topics is because they have a very tight connection to dark matter underneath it. And although I won't focus as much on it today, I would like to actually kind of motivate it this way. That, for example, for stellar streams, studying the density variations in stellar streams can tell us about those small dark subhalos that we would not be able to see otherwise, that might have kind of caused gaps in stellar streams, which is why finding these stellar streams is critical. At the galactic center and the galactic halo, studying the density profile of dark matter in the inner galaxy can tell us something about baryonic feedback and galaxy evolution in general, but also about the particle nature of dark matter. This is quite similar to the topic in dwarf galaxies, although they are a much cleaner background, so it will not be affected as much about baryonic feedback. And finally, in the solar neighborhood, the way that I like to think about it is that studying the merger history of the Milky Way, especially next to us, where we have the most data, can tell us about the phase space distribution of dark matter. So studying, for example, the velocity of stars and using simulations to connect them to the underlying dark matter is quite important. And this not only helps us understand galaxy evolution in general, but also can help us understand help us set up our direct detection experiments correctly by knowing exactly what to expect for dark matter. So Although right now this looks wonderful and beautiful, the data is not so clean. Although with the Gaia revolution, we have the best kinematic data set of all time, and we can see our galaxy looking like this. And although it's beautiful and amazing, it is just a big mess because that's what galaxies are like. And what we want is to understand the structure and really sift through this data, this kind of high background data that has uncertainties, just like any science, to figure out the structure underneath it. So what we would like to do is, for example, go through the Milky Way and identify these structures. You can see here the stellar streams. These little boxes are dwarf galaxies. The stars are globular clusters that we find. And although it is a huge, big mess, we can develop these methods to really uncover all of the structure in our galaxy. So in this AI signal processor part of the talk, what I would like to discuss is two different parts. So finding these stellar streams and finding the stellar kinematic structure in the solar neighborhood. So the challenge here is sifting through a lot of noisy data. And although it's, again, the most amazing data that we have, it still has some noise, it has some background, some things that we don't want. And the common challenge between the stellar streams, which tend to be a little bit further away, and the local stellar structure is that we have low signal to noise. For example, for the stellar streams, they are just going to have to be sitting there with a background of, or foreground rather, of all the galaxy and things that we have to go through. And for the kinematic structures in the solar neighborhood, most of them are going to be dominated by the disk, which is, although interesting in its own right, what we want is to understand the merger history, so the accreted component. So the way that we kind of go around this is trying to find properties of the data that we can use. So for example, for the stellar streams, we need to find the linear structure in position space, because we know that, stellar streams tend to be extended in the sky. So that's something that we can use. And for the solar neighborhood, we want to find things that are clustered in velocity or action angle space, just because the properties of mergers and structures are going to kind of give us those clumps in there. So I've done some work with my group in these two areas that I would like to kind of introduce, but these are just examples of kind of a much bigger field. So starting with the stellar streams, what we built is, with my collaborators, is Via Machina. So this is a new algorithm that is based on anomaly detection to try to find the stellar streams. So the way that we do that is by looking at the sky with Gaia DR2, and we kind of break it into patches. And then we look at the space of positions, proper motions, and colors to try to identify anomalous structure. So what's going on? And the way that we do that is by using normalizing flow. So for example, if you mask a region, which is kind of like a window that we scan through, and then we look at the distributions otherwise. So we have what we call a control region. I can see the data on this side as well as the data on the other side. And I can make a prediction for what's in my masked structure. So for example, I expect it to kind of go around the same way. This is the probability of the control region. What I can see then is by unmasking is, oh, there is a spike in there. So what you can do is take a ratio of what you actually see versus what you expect and try to see if it is more than 1 or, logarithmically more than 0. That tells you that there is something anomalous in there. So this is a method that actually has been initially presented in this work, Nachman and Shi, in 2020 to use for Large Hadron Collider searches. And the reason that this collaboration, Cosmic AI, also is interesting is because we use similar methods for a lot of different problems. And that's why it's very interesting for us to kind of cross-talk to each other. So going through this, we can make a cut on this kind of specific ratio and try to find the anomalous structures. The thing is, as of now, if you just stop there, you would find a lot of anomalous structures, including, for example, globular clusters. And the reason for it is, indeed, they are anomalous compared to the background. So what you'd want is to use something specific about your data, which is, for example, the Huff transform. So if I do just a cut on R, and of course here I'm using kind of like the most obvious of the stellar streams. I'm going to go from data that looks like this to something that has that linear structure. But I need to add this Huff transform to say that I'm looking only for linear structure specifically, and compute, of course, a linear significance and etc. So I'm using something that I know physically motivated or physically informed from my data to actually play with that. So the cool thing is that for the most prominent streams, especially, for example, like GD1, the common stream, we can kind of compare our analysis, which is here, found in red, to the selection that is computed in the literature, for example, here, and we see very similar density variations. And that's very interesting because, for example, this gap right here could have been caused by a dark subhalo or a dark structure that helps us understand the physics. And the extra interesting thing here is that we were not really kind of tuning to the right membership, but we were really more tuning towards the anomaly detection. So actually, at the end of our work, we found about 102 streams with Gaia GR2, and we ran the same pipeline on Galaxia, which did not have any streams, or we made sure it didn't have any, and we computed a false positivity rate, which means that out of our 102 streams, we expect about 90 of them to be true positives, which is really, really interesting. Currently, we really have to follow up on these streams, and we're trying to automate kind of cleaning up the membership by looking at the different patches in the sky. So hopefully, with a lot of this work, we kind of can speed up and leverage the power of AI to go through a lot of data, but also including kind of anomaly detection, including the properties of the data itself, and in particular, this is the linear structure. And the power of this method is that we did not use a particular isochrone, we did not use a gravitational potential of the Milky Way, we just kind of got it to sift through the data, tried to pick up what does not look like it belonged there. Moving on to the solar neighborhood. So for the solar neighborhood, we have kind of somewhat of a similar exercise, but now what we want is to look for stellar kinematic structures. We're not looking for actual kind of stellar streams, but really something that stands out in velocity space. And for that, we usually use clustering algorithms. And if you could see this, just this, your brain is actually really, really good at finding structures. And indeed, you'll be able to see, for example, this structure right here, 1, 2, 3, 4, 5, maybe something 6 here. All of this is going to be classified as noise. So although our brains are really, really good at finding clusters, they are kind of limited to 2 dimensions. Going into 3 dimensions and more, it's really, really hard for us to find that. So we need to automate it. However, something that people tend to find quite frustrating with clustering algorithms is that different clustering algorithms are going to give you different things, right? So for example, k-means is going to group this red with this one, this orange here with this, something that is not quite intuitive. Well, for example, HDV scan in this particular case actually is going to do mostly what your brain does, which is why it might be a better choice for this particular data set. The choice of the algorithm that you use, it really depends on the properties of the data. And this is why, for example, we're not going to go all in like, oh, AI is going to take our jobs, but there is like this interconnection between the AI methods and kind of like the physics or the astrophysics that we know. So for example, in this particular problem, I know that there will be noise to my data set. There is no way I can clean it up beforehand. The different structures will have different sizes, different shapes, and different densities. So whatever algorithm I'm going to pick needs to do and follow these properties. Traditionally speaking, what we've been doing before is to kind of use physically motivated cuts in different spaces, which means that I can take the action angle, and the reason for it is because these are very physically motivated, because if you assume that the gravitational potential of the Milky Way doesn't quite change, then things that are the same get clustered around the same thing. So for example, this one is one thing, this is another thing, and this is what has been kind of happening really in the literature before, where it's not just in the action angle, you can kind of use metallicities or chemical abundances and kind of slice it and dice it and have like a lot of different kind of human effort that goes into it to make sure that things are as clean as you can. However, I think that there might be a reason for us to automate this process because, again, as the dimensions increase, it's really hard for our brains to be able to kind of sift through this correctly. So the way that we did this is work that was led by my student Xiaoyu, who recently graduated and actually will be joining the University of Virginia, partly funded by Cosmic AI. And what Xiaoyu did is looking at the action angle variables and as well as kinematics right here, and trying to see, to answer the question, okay, we can throw a clustering algorithm at this and all right, it will spit out something. But what we wanted to do is understand the errors. So we wanted to make sure that whatever we can get is stable under measurement uncertainties. So there are a lot of measurement uncertainties for different data sets, right? And what we want is to try to figure out that whatever cluster we have is quite stable. So the way that we did this is by reclustering a lot of time over different realizations that show for that few clusters are indeed stable, right? So the way that I think about it is kind of like shaking your data a little bit. And the way when we implemented that, we actually found that these red groupings of stars, including this one, which actually ended up being NGC 3201, a globular cluster, tend to be always present, always clustered, and in most cases not classified as noise. So we think that they are definitely there. So then we can run our HGB scan again on these very, very kind of not noise or less likely to be clustered as noise, and we can find those different structures in the solar neighborhood. So this is interesting, and it has pros and cons, of course. So the pro is that whatever we got here, we're pretty certain that indeed they are clusters, that it's not just because of measurement noise and all of that, which is amazing. Of course, it comes at a cost where my HGB scan kind of broke our structure too finely, which is why after the fact we did some post-processing, trying to understand and incorporate chemical information to put things together. Is this whole thing one thing, or is it multiple objects? And actually the literature is divided on this at all. So again, what we wanted to do is kind of incorporate the properties of our data, and in this case, measurement uncertainties, to kind of enable the clustering algorithm to give us exactly what we want and give us something robust, which is kind of key, especially in using AI in science. So moving on from the AI signal processor, let's try to kind of go into archaeology. So this here is going to be kind of moving on a little bit from the unsupervised to something that uses simulations and is supervised. So for that, we need to use simulations. And not only do we need to use simulations, but we need something that kind of resembles what we would see in data. And then in this particular case, we're going to use Ananke, which is a synthetic survey based on Gaia, and in particular, we're going to use the one that is based on one of the data releases of Gaia, where this is answering the question, what would Gaia see if it lived in one of the fire simulations that we live in? And you can see that it does pretty good, or at least we're not trying to exactly replicate the Milky Way, but it does look pretty realistic. So what we want here is train on simulations based purely on kinematics and label Gaia stars as accreted or in situ. And the reason that we do that is because that way we can kind of get rid of the in situ stars and look for new and novel, interesting accreted structure that tell us a little bit about the merger history in the Milky Way and subsequently what the dark matter is in the solar neighborhood. So we've done that a while back, and kind of once we do that and cut on the score, etc., we are able to see this structure. So this is in kinematic space and spherical coordinates. So we have VR v phi, VR v theta, and v theta v phi. And there are things that kind of really jump at you like this. So for example, this is the background halo, and this interesting structure is the Gaia Enceladus. So the Gaia Enceladus is actually a discovery that was found without AI. And it is this merger that hit the Milky Way about 6 to 10 billion years ago with a mass of 1 to 10% the mass of the Milky Way. And it kind of looks like this. This will explain kind of why the initial name was not Enceladus, but rather the Gaia sausage, and now we refer to it as the GSC altogether. And it is this galaxy that has merged into the Milky Way and kind of landed into this extremely radial orbits, right? So imagine that we live somewhere around here. So we can see these stars that are going in and out of these high orbits. So that was amazing. And again, it's good that whatever AI thing we use actually does replicate such a huge structure. But what we found that was interesting is this extra structure right here that we call Nyx. So Nyx is the Greek goddess of the night, which was really, really fun to find and play with. And it's basically this collection of stars that are kind of going through this whole neighborhood. And they are at kind of radial orbits, but like they're prograde radial orbits. And the reason this is interesting is because traditionally, and up until then, when we looked at it, we would not be able to have seen this because it would have been sitting under the disk, right? The fact that they have co-rotation, for example, you can see it like this, where the sun co-rotates like this, and they do too, means that they were consistently cut out of any analysis. They do extend a little bit further from the disk, as you would see here. And the reason that this is interesting is because we can understand, I mean, it's an interesting question in terms of the formation of the Milky Way itself. And what is this origin of this Nyx structure? The two possibilities are either that it's a merging galaxy, and it's something that kind of has imprinted in our Milky Way a long time ago, or that it is the cause of a disk perturbation, which means that something has hit the Milky Way, for example, Sagittarius, but a lot of other things have hit our Milky Way and kind of caused these ripples right here. So if Nyx is a merger, it would actually be a very interesting one because it would be this prograde merger that kind of get tucked in kind of co-rotation. And this will have a lot of impact in terms of direct detection because it will enable us to see the very, very, like to probe the high mass dark matter. But unfortunately, I'm not going to be able to get into that. Okay, so I think I need to speed up for the rest. So the interesting thing that we can do here is observe the chemical abundances, and unfortunately, you end up with we did, and what we found was that it is basically it's inconclusive, which is the right way of doing things. But okay, so can we extract even more information? So instead of me trying to find structures and then try to replicate to figure out exactly where they came from, can I just like put all of this together? Well, people have done that in different ways, including using supervised learning and the properties of globular clusters that kind of help us figure out, okay, this is the Milky Way and the Kraken and the Helmi streams, and each one has different sets of globular clusters that kind of help us set up its original mass. The way that I wanted to kind of look at it is slightly differently is using graph neural networks, because, for example, as the work of Wu and Jespersen here, it enabled them, when they use graph neural networks, to actually study the environment of galaxies and how that impacts galaxy evolution. So the one thing that I would like to add in this is that, well, for example, we need to, again, with the same theme of adapting our algorithm to the properties of the data, and this particular case is symmetries. So the setup that I'll be describing very, very fast is using equivariant graph neural networks to make sure that the symmetries, and especially the velocities, are all rotating the right way. So the way I do this is kind of set up this structure of the different stars and looking at their velocities trained on a luster CNG. And one of the considerations, of course, is that of domain adaptation. I'll move on a little faster towards the end. So this is to kind of motivate the reason that we need to look into dwarf galaxies. And for astrophysics, this is interesting because we need to understand how these small galaxies form. For particle physicists, understanding whether or not that's a cusp or core can tell us about the different particle nature of dark matter, and also about what is the signal that we would expect. Since I don't have much time, I will just kind of go with, it's very, very hard to do this using genes analysis. And indeed, if you were, for example, the traditional method, which is what we call genes analysis, requires about 10,000 stars or 10,000 data points to really get the right distribution, which unfortunately is very, very hard to get. But that's even in the best of cases for the massive galaxies And for the smallest galaxies, if you have any uncertainties, it's just everything is breaks loose. So the way that we want to tackle this is really use the data to your advantage. So here is what the data looks like. Well, actually, this is what it actually looks like. You have different positions and line of sight velocities. And what you would want is to take all that information and turn it into a density profile of dark matter to figure out if are we in the cuspy or core distribution. So to leverage that, my former student, who is now a Sierra Fellow, Tree Nguyen, who is in the room, has worked on leveraging the structure of graphs in dwarfs, and what we built is Graph MPE. So Graph MPE is this graph neural network structure that we tested on idealized and hydro sims, but I'm going to leave all the details to Tree's talk at 10:50. So let me just close by saying that there are a lot of interesting applications for AI in the world of dark matter, and especially in the world of going from this mapping of stars and dark matter and trying to understand what's kind of hiding beneath it. And the interesting thing that I would like to leave you with is that with the AI revolution, we really need to work with people. We really need the work of people at the intersection of both fields to build and adapt new methods to work for astrophysics, especially for our data and the science questions, so we can have rigorous, interpretable science and science results that we can trust, but things that can actually be able to kind of go through the data revolution that we're getting. So with that, thank you so much for your attention.
Okay, so now we have time for a couple of questions. Yes, Peter. So Peter was asking about the equivariant graph neural network and talking about what type of equivariances you have and what type of symmetries you might have there.
Right. Thank you for the question. So basically the way that we have it's Euclidean structure. So it's mainly about the different features. So I use the positions to set up the network and the graph neural network. And the features that I have are the value of the potential and the metallicities, which are scalars, but the critical thing is the velocities, which I want to make sure that they transform as vectors while I rotate this. Does that answer your question?
Yes, thank you. So can I ask you a question about the simulations you are using? So in the simulations, we know that they are not exactly replicating the observational data. How do we guarantee that what you are learning from the simulation can be transferred and used for the observational data without inducing any sort of biases?
Right. So I think that is the critical part that we have here, and that is one of the considerations of like this out of domain adaptation. So for the dwarf case, we're also training on simulations and realizations, but I'm going to let Tree kind of address that when he kind of gives you the full rundown. But for something like this, the way that I'm going to incorporate it is that we're going to use multiple different simulations. So in particular, we're going to train with Illustrious DNG. A subset of Illustrious, we have like a different kind of work that looks for a subset of the galaxies that have similar properties as the Milky Way. So for example, the presence of the Gaia sausage Enceladus or an LMC. And then what I'd like to do is also kind of include information from Fire, and I have other work that kind of shows that how Illustrious and Fire are both in the two extremes in terms of baryonic feedback. Hopefully that we would kind of help kind of narrow down that the Milky Way is in between. But I think it's going to be an interesting work to figure out that we're really not completely out of it, out of like domain. And I think that is going to be the biggest challenge. These are at least like my first ideas on how to deal with it.
All right. Thank you, Lina. Any other last minute question? All right. Let's thank Lina.
Thank you so much, guys. Thank you.